fundamental question is, are there other planetary systems, and are any of them like our own solar system? And of course, you can look up in the sky and see literally thousands of stars. There are maybe 100, 200 billion stars in our Milky Way galaxy. And you could say, well, of course there are other planetary systems, but you have to find them, right? It's just an assumption that there are other planetary systems, so we need to find them. So here's one way of finding them, direct imaging. The trouble is stars are very bright. Planets intercept only a tiny fraction of the star's light, so you need to diminish the star's light in order to have a hope of seeing the reflected light from the planet or the thermal emission that it produces because it might be warm. The stars are more than a billion times brighter. So that's easiest to do from above Earth's atmosphere, and the Hubble Space Telescope has been doing that, and perhaps its most famous success has been this star called Fomalhaut, which seems to have a little dot moving around it, and there have been subsequent measurements in 2010 and 2012 that show it nicely progressing forward. And so this might be a Jupiter-sized planet or something orbiting this star. There's a debris disk or ring which might be in the process of forming additional planets. The star itself has been blotted out by an occulting screen right here. Anyway, that's been done with the Hubble. A few others have been found with the Hubble as well. By using the twin Keck telescopes in Hawaii, astronomers have also found a few planets by direct imaging. Here's the star whose light has been suppressed by a factor of 1 billion or so, and that process isn't perfect, and so you get a bunch of residual stuff. But here are 3 dots that appear to be moving around that star. So that's probably a bunch of exoplanets. A technique that has yielded many, many more exoplanets, indeed hundreds of them, is the Doppler wobble technique. Basically, a star and a planet orbit their common center of mass. It's not strictly speaking true that a star is stationary and a planet orbits the star. They orbit their common center of mass. It's just that the star moves a lot less than the planet does because it's a lot more massive. Well, if you take spectra of the star repeatedly, that is, spread out the light, you can look at these absorption lines, which are produced by elements in the relatively cool outer atmosphere of the star. And when the planet is going away from you, the star will be coming toward you, and so the light will be Doppler blue shifted. Conversely, when the planet is going toward you, the star will be going away from you, and so the light will be red shifted. These shifts are not big. Here we spread out the spectrum a lot in order to try to detect this reflex motion, and it's a very, very small motion. So here we're going to look at one of these absorption lines with a magnifying glass. Over time, the absorption line goes back and forth, blue shift, red shift, blue shift, red shift. And here we exaggerate the effect by about a factor of 1,000, in fact. So this shifting of light among the pixels is much, much more subtle than this. However, you have thousands of lines, as you can see from that background spectrum, with which to do this procedure. And in fact, you can detect motions that are the equivalent of a person walking at a normal pace through the room. That's how fast the star is moving. This was first done in the mid-1990s when the response on the cover of Time magazine was, is anybody out there? How the discovery of 2 planets, it's now up to thousands, but anyway, the discovery of 2 planets brings us closer to solving the most profound mystery in the cosmos. You can see this was a big time story, more important than Dole drops, Clinton rises, because that kind of stuff happens every 4 years, and half of that headline could even be relevant this time around. Anyway, you might say, well, you've read plenty of scholarly articles that show definitive evidence for the existence of extraterrestrials, even intelligent ones. Because look, here's alien backs Arnold for governor, right? So hasta la vista, Gray Davis. Well, don't believe absolutely everything you read. Now, in the early years, the Shane 3-meter reflector at Lick Observatory was used to find lots of these things. I believe 70 of the first 100 exoplanets discovered were discovered with this telescope. And here's an example of the signal that you got. The velocity, in this case meters per second, versus time. And you see you need a lot of data over a long period of time in order to see these oscillations. You see the points don't fall at a constant speed. They vary, and you can fit periodic functions, and then you suspect that there are planets, so you start taking data more frequently, and now you really suspect that there are planets, and so you take lots and lots of data verifying them. Well, you see the most obvious oscillation has a period of 0.7 years. That's caused by a planet having roughly twice Jupiter's mass. But there's another periodic function here with a period of 4 years that happens to be caused by a planet having roughly 4 Jupiter masses. And the signal, a very high frequency signal from a 4.6 day orbital period planet, has been removed from these data, but it's there as well. So here's the planetary system around the star Upsilon Andromedae. There's this 4 Jupiter guy out here, 2 Jupiter guy there. Here are the orbits of Earth, Venus, and Mercury in comparison. And then here's this guy that goes around in 4.5 days. And one of the big surprises in the early study of exoplanets was the discovery of these so-called hot Jupiters, massive planets that orbit very, very close to their parent star in a matter of days. Artists' impression is that this planet is actually being evaporated away. This is probably not a good planet on which to find intelligent life or life of any sort. Well, this plot simply shows a subset of the planets that have been discovered with this Doppler wobble technique. There are 700 or 800 of them now. There's 200 in this graphic. One important point is that the exoplanet masses that you measure from the Doppler wobble technique are minimum masses. And that's because you don't know, in general, the orbital inclination. And all you're measuring is the radial velocity of the star. And that being only one component of the total velocity, thus only gives you a minimum possible mass for the exoplanet causing that reflex motion. Nevertheless, you can play statistical games, and on average, these things aren't going to be much more than about twice as massive as the one you found. And so these masses modulo some factor of 2 are pretty good. The other major technique, and this one has been getting a lot of press in the past few years, is planetary transits. In our own solar system, we see this once in a while, twice, spaced by an interval of 8 years, followed by nothing for more than a century. Venus actually passes between Earth and the Sun. And so if you were measuring the Sun's total brightness at this time, you would find that it's a little bit less than normal because Venus is blocking part of it. So if you have a planetary system around another star and the orbital plane happens to be along our line of sight, then you have the potential for planetary transits. Only roughly 1% of planetary systems are going to have the right orientation at random. Nevertheless, if you monitor enough stars, you should start finding systems like this. If you do, it's really wonderful because there's the potential of measuring the atmosphere of the planet. So here we have the planet transiting the star, and let me just stop it here because I want to talk about it for a few seconds. The planet blocks the star's light. The atmosphere is transparent to the star's light, but only selectively. There are certain wavelengths at which the light could be blocked, okay? This atmosphere is transparent, but there are certain wavelengths at which it's not transparent, okay? And so by measuring the spectrum of the star during a transit and comparing it with the spectrum of a star not during the transit, you could hope to see absorption lines produced by the atmosphere. And that was first done for this star using some exquisite data taken by the Hubble Space Telescope. Sodium was detected in the atmosphere of that planet. Now, planets are small compared to stars in general, so the decrease in the amount of light is pretty tiny. For a Jupiter-sized planet, it's about 1%, because Jupiter is about 1/10 the diameter of the Sun, so the area is about 1/100th. That already is a pretty hard thing to measure, a dip of 1%. Earth is 1/100th of the Sun in diameter, so in area it's 1/10,000th, so the dip is 1/100th of a percent. That's really hard to measure, especially from the ground because of twinkling and basically turbulence in Earth's atmosphere. So the best way to do it is to go to space, and there the Kepler Space Telescope has just caused a revolution in exoplanet research. Here's an artist's conception of it, looking at one of these randomly oriented planetary systems that happens to have its plane along our line of sight. Now, it looked in a region right at the boundary of Cygnus the Swan and Lyra the Harp, not right into the Milky Way because there would be too much crowding there, but not way outside the Milky Way because there wouldn't be enough stars. they measured 156,000 stars' brightness basically every minute. And most of the time, they're not doing anything interesting. But occasionally, a planet might block part of the star's light in 1% of the cases. And here are some of the early results that were found, just fantastic. And the early results were found after just a few days, and so these are biased toward being the planets that have very short orbital periods. Now, with 3.5 years worth of data, you can start finding planets that are farther out. And you can even find multiple planet systems by looking at these different periodicities. This guy is the same as that, but here's another planet marked with a blue arrow, and here's another planet marked with a purple arrow, and you're not even sure about that planet yet because it's generally agreed that you need at least 3 detections. Anyway, Kepler has been spectacularly successful, not just at finding the big ones, like in the early data that I just showed, but also more or less Earth-sized planets or even smaller than Earth. They've gotten down to Mercury-sized planets. Here's the Kepler 20 system compared to Earth and Venus. Here's the Kepler 37 system. Look at 37b here. It's sort of between the Moon and Mercury in size. So Kepler has found thousands, like 3,500 candidate exoplanets, of which over 90% are thought to be genuine exoplanets. There are other tests you need to do to verify them. Well, then, of course, you get to the next question. You want the ones that are habitable. Not so close to the star where liquid water would evaporate away, not so far from the star where liquid water would be frozen, basically, but sort of in the Goldilocks zone, the just right zone. We're looking for water because at least life as we know it, not counting AI and stuff, is based on water. And so as a first guess, let's look for where the water is. And so that's what we want to find. Well, among the Kepler statistics, 3,500 candidates, they now know that 1 in 5 sun-like stars has a roughly Earth-sized planet in this Goldilocks zone. By the way, being in the habitable zone obviously does not mean that it's for sure inhabited. Doesn't even mean that there's liquid water. You need a proper atmosphere to have liquid water, but at least there's the potential of having liquid water. Roughly 10 billion Earth-sized planets in the habitable zone around sun-like stars. That's good news for Jill. 40 billion if you include the so-called K and M stars, the stars that are smaller than the sun. They're even more numerous than the sun. In fact, our galaxy is full of M stars. And so 40 billion potential Earth-like planets in our own Milky Way galaxy, not to mention all the other galaxies. And this doesn't even count the moons around some planets that might be habitable, like Enceladus around Saturn and Europa, perhaps. And then the latest big news, not the very latest, Jill will tell you about that, but the latest big news that many of you heard about last week was that astronomers using telescopes primarily at the European Southern Observatory in Chile, a 3.6 meter telescope, using the Doppler wobble technique, detected a probable, roughly Earth-sized planet, maybe 1.3 times Earth's diameter, but that's roughly Earth-like, orbiting with an 11-day period around the nearest star. So unless a more nearby star is found, and that's unlikely in my opinion, because we've searched far and wide and haven't found any, this will be the closest habitable planet ever found, right? Because there is no more nearby star. This one's 25 trillion miles away, 40 million kilometers. Here's a Hubble picture of it, not that stars have spikes growing out of them. This is a diffraction pattern, but nevertheless, the star has become even more famous than it was before. And this was just last Wednesday, folks, my first day of classes at Cal, and I told the students that almost not a day goes by that there's not some astronomy story, and usually every week or certainly every month there's a big story, and that day there was that story. So here's their graphic. It's not the greatest graphic, but it shows, because it's too dark, but here's Mercury's orbit, here's Proxima Centauri b. It's so close to Proxima Centauri, yet in the habitable zone, because Proxima Centauri is a very low luminosity star. And so to be heated to an Earth-like temperature, the planet obviously would orbit pretty close to the star. Interestingly, the Alpha/Proxima Centauri system is the one that made headlines earlier this year because Yuri Milner and Stephen Hawking and Mark Zuckerberg and others are hoping to maybe send a little iPhone-sized spacecraft at 20% of the speed of light toward this system. snap some photos of it and send them back to us. So that'll be fantastic if it happens. I don't know that I'll be alive. I probably won't be unless Ray's nanobots save me. But anyway, this is a golden age of exoplanets, direct imaging, Doppler wobble, planetary transits, and other techniques that I didn't have time to mention. Potentially habitable Earths are being found, and maybe one of these days we will find Yoda. Okay, thanks very much.